Welcome back. In the previous video, we have seen that a two decision variables linear programming problem can be easily solved by graphical method. But to solve a three decision variables linear programming problem, we have to use a more general method called as simplex method. To understand the procedures in solving by using simplex method, we need to know some basics. So, we shall learn some basics first. Algebraic representations of the linear programming problem always has less or equal number of equations than the number of variables. For if the number of equations are same as the number of variables, the equations are consistent, the system has only one solution. For example, consider the equation x plus y is equal to 2 and x minus y is equal to 0. Then solving these equations gives only one solution with x is equal to 1 and y is equal to 1. But if the number of equations in the system is less than the number of variables, the equations are consistent, the system will have an infinite number of solutions. For example, if we consider only one equation with the two variables, that is, say x plus y is equal to 2, then solving which we get y is equal to 2 minus x. Then depending on the value we choose for x, we get different values for y. That means we get an infinite number of solutions. In graphical method, we have seen that the required solution is obtained from one of the corner points. To count the number of corner points algebraically, set n minus m variables of n variables as 0, where m is the number of equations. The resulting solution is called a basic solution and corresponds to the corner point of the solution space. Hence, the maximum number of corner points is given by the combinations of m items taken out of n items. For example, consider the linear programming problem with two variables. Maximize z is equal to 2x plus 3y. Subject to the constraint C1 given by 2x plus y less than or equal to 4 and C2 given by x plus 2y less than or equal to 5 and the non-negative constraints x comma y greater than or equal to 0. The figure here illustrates the solution of this problem found graphically, but algebraically we can represent the constraints of this problem as 2x plus y plus s1 is equal to 4, x plus 2y plus s2 is equal to 5 with x, y, s1, s2 greater than or equal to 0, where to get an equation s1 and s2 are used to fill the left hand side and that is less than or equal to the right hand side value. These variables that are used to fill the left hand side, that is less than or equal to the right hand side value in order to get an equation, are called as slack variables. This system has two equations and four variables. Hence, by the above procedure, we have to set 4 minus 2 is equal to two variables as zeros. If we set x is equal to 0 and y is equal to 0, then we get s1 is equal to 4 and s2 is equal to 5. That is, at the origin point A in the figure, we set s1 is equal to 4 and s2 is equal to 5. Hence, we have obtained the solution at the origin. Here, the 0 variables are called as non-basic variables and the remaining are called as basic variables. Here, some of the points are not feasible. From the graphical solution, you can notice that E and F are not a part of the feasible region and hence the corresponding solutions are not feasible. Hence, A, B, C and D are the four corner points that are feasible. Now, by using the objective function, we can track the point that gives the optimum solution among these 4 points. Simplex method is designed to perform iterations in order to find the optimum solution for the given linear programming problem. Initially, we assumed x is equal to 0 and y is equal to 0. Since objective function depends only on x and y, initially the value of the objective function is 0. If either x increases or y increases or both increases, the value of the objective function will also increase. But the simplex method is designed to increase the value of one of the variables in the objective function in every step of calculation. Graphically speaking, we can either increase the value of x along the x-axis or increase the value of y along the y-axis. That is, we can increase the value of x by 2 along the x-axis to reach the feasible corner point D, or we can increase the value of y by 2.5 along the y-axis to reach the another feasible corner point B. Among these two options, the best option is to increase by 2.5 units to get the better maximum. That is, 2 times 0 plus 3 times 2.5 is equal to 7.5 at B, which is better than 2 times 2 plus 3 times 0 is equal to 4 at D. That is, now x is equal to 0 remains as non-basic and y is equal to 2.5 becomes basic, and hence S1 is 1.5 remains as basic and S2 is 0 becomes non-basic. That is, we obtain an improved value 7.5 at B for the objective function, which is previously 0 at A. Now repeating the procedure for the point B, the nearest neighbors to B are the corner points A and C. Since B gives a better maximum than A, do not choose A, choose C and test. The objective function value at C will be 2 times 1 plus 3 times 2 is equal to 8. This value is more than the previously obtained 7.5. That is, x is 1 becomes basic and y is 2 remains as basic, and hence S1 0 becomes non-basic and S2 0 remains as non-basic. The neighbors of C are B and D. Since C has better maximum than B and D, the maximum value is 8 when x is equal to 1 and y is equal to 2. The simplex method follows the same flow and is illustrated here. The highlighted cells clearly project the same transformation that we discussed with the help of the graphical representation. If these simplex tables are to be obtained without the help of graphical representation, then we have to calculate as follows. Step 1. Express all the constraints as equations except the non-negative constraints of the given linear programming problem. Hence we have maximize z is equal to 2x plus 3y subject to the constraints 2x plus y plus s1 is equal to 4, x plus 2y plus s2 is equal to 5 with x, y, s1, s2 greater than or equal to 0. Or equivalently, maximize z is equal to 2x plus 3y plus 0 s1 plus 0 s2 subject to the constraints 2x plus 1y plus 1 s1 plus 0 s2 is equal to 4, 1x plus 2y plus 0 s1 plus 1 s2 is equal to 5 with x, y, s1, s2 greater than or equal to 0. Note that the coefficients of x are 2 and 1, the coefficients of y are 1 and 2, the coefficients of s1 are 1 and 0, and the coefficients of s2 are 0 and 1 respectively in the first and second constraint equations. By representing the coefficients in the matrix form, we have 2, 1, 1, 2, 1, 0, 0, 1. Here, the submatrix 1, 0, 0, 1 consists of the basis element 1, 0 in the first column and 0, 1 in the second column. Since S1 and S2 corresponds to the basis, we can refer to S1 and S2 as basic variables. In step 2, since S1 and S2 are basic variables, set the non-basic variables as 0. That is, by setting x is equal to y is equal to 0, we get the solutions for S1 and S2 as 4 and 5 respectively. So with this solution, we set the initial simplex table. In this table, CB stands for coefficient of basic variable, where the CB column elements are taken from the objective function. BV stands for basic variable, where BV column elements are taken as basic variables. The column headings x, y, s1, s2 are meant for display of the respective coefficients from the constraint equations. Solution column is meant for the display of the solutions of the respective values of the basic variables that are displayed under the BV column. The numbers given above the variables x, y, s1, s2 are the coefficients of the respective variables in the objective function. Now, since s1 and s2 are the basic variables, we have entered them under the BV column. Also, notice that by setting x is equal to y is equal to 0 in the first and second equation of the constraint, we get s1 is equal to 4 and s2 is equal to 5. So, we have entered 4 and 5 as solution values of S1 and S2 under the SOL column. The coefficients of x are 2 and 1 in the first and second equation respectively and are entered here as 2 and 1 under the x column. Likewise, we have entered 1 and 2 under y column, 1 and 0 under the S1, 0 and 1 under S2. Since S1 and S2 are basic variables, the coefficients taken from the objective function are entered under CB column. The coefficients of S1, S2 in the objective function are 0 and 0, and hence the CB column is entered with 0 and 0. What remains to explore in this initial simplex table is the row of net evaluations that is denoted as NER. These values will appear only under the variables column x, y, s1, s2. The number appearing under SOL in the NER row is the value of the objective function at that stage of computation. To find the net evaluation value minus 2 under x variable, multiply the respective elements of CB and x, sum it up and subtract 2 that is given above the x variable. That is 0 times 2 plus 0 times 1 minus 2 is equal to minus 2. Likewise, repeating the same procedure for y, s1 and s2 columns also, we have 0 times 1 plus 0 times 2 minus 3 is equal to minus 3, then 0 times 1 plus 0 times 0 minus 0 is equal to 0, then 0 times 0 plus 0 times 1 minus 0 is equal to 0. The same calculation can be extended for the SOL column of the NER also by assuming that there is no element to subtract, that is 0 times 4 plus 0 times 5 is equal to 0. So, note that this value is not the net evaluation value, it is the value of the objective function at this stage of computation. Hence, we have the 4 NER values minus 2, minus 3, 0, 0. The most negative among these 4 is minus 3. And this indicates that from the origin with 0, 0, we have to move along the y direction to choose the best corner point that is adjacent to 0, 0. That is, y will assume some value other than 0 and hence becomes a basic variable. That is, y enters the basic variable column and is referred to as the entering variable, or equivalently, the variable corresponding to the most negative in the NER is the entering variable, and the column corresponding to this variable is called as the entering variable column. Now, if y has to enter the basic variable, any one of the S1 or S2 must leave from the basic variable column by becoming non-basic. To identify that, whenever the element of the entering variable is not negative or 0, divide the SOL element by their respective entering variable column element, that is, find 4 by 1 and 5 by 2. Among these two, 5 by 2 is the least and we call this value as the minimum ratio. Hence, S2 will become non-basic and will leave the basic variable column. We call S2 as a leaving variable and the row corresponding to the leaving variable is called as the leaving variable row. Hence, we have to transform the simplex table in such a way that y becomes the basic variable and S2 will become a non-basic variable, and then list the transformed values in the new simplex table. This is possible only if the column elements of y become 0 in the first row and 1 in the second row. At present, these elements are under S2. We can achieve this by using appropriate row transformations. We also refer to the element common to both the entering variable column and the leaving variable row as the pivot element. Here we find that 2 is the element common to both the entering variable column and the leaving variable row, that is 2 is the pivot element. Our objective here is to shift the basis of S2 to y, which makes y a basic variable. Now consider the next successive simplex table in which y is replaced for S2 as S2 is non-basic and y is basic. Also fill the CB column with the respective coefficients of the basic variables from the objective function. Now divide the leaving variable row including the element of solution in the same row by the pivot element, and hence we get 0.5, 1, 0, 0.5, 2.5. That is, we have given the row transformation to the second row of the previous table by using the formula R2 previous by 2 in order to get the new values of the second row of the current table, represented as R2 current. Always use this new row as the key row to transform the remaining rows, so that the remaining rows of the entering variable column y are zeros. Next, transform the row R1 of the previous table to get the R1 of the current table by using the formula R1 current is equal to R1 previous minus R2 current. This is formulated in such a way that every other row element of y column other than the element 1 in R2 current of the y column becomes 0. So by this process we have transformed the elements in such a way that the basis 0, 1 held by S2 is handed over to y, and hence it makes sense that now y is a basic variable. The second simplex table is shown here. Now repeat the procedure of finding the NER in the second simplex table. Also compute the value of the objective function as mentioned in the initial simplex table. Hence we have the simplex tables as shown here. Since minus 0.5 is the only negative element among the net evaluation values minus 0.5, 0, 0, 1.5, the most negative is minus 0.5. The corresponding element is the entering variable column, and hence the entering variable here is x. Now to find the minimum ratio, divide the elements of SOL by the corresponding elements of the entering variable of the column, that is 1.5 by 1.5 and 2.5 by 0.5. This simplifies to 1 and 5, which indicates that 1 is the minimum ratio, and hence S1 leaves the basis and 1.5 is the pivot element. To proceed to the next iteration, form a new simplex table such that x is a basic variable that is replaced for S1. Hence, the basic variable column will have x in the first row and y in the second row. Also fill the CB column with the respective coefficients of the basic variables from the objective functions. Since 1.5 is the pivot element, divide the elements of the first row by 1.5. That is, R1 current is equal to R1 previous by 1.5. To get 0 elsewhere in the same column, apply the row transformation R2 current is equal to R2 previous minus 0.5 times 1, where 1 is the key element in the new table, which is in the pivot position of the old table. Hence, we get the new simplex table. Also computing the net evaluation values, the values of NER are 0, 0, 0.333, 1.333. They are all non-negative. So no more iterations are possible, and this becomes the optimum table. Hence, the solution for the given linear programming problem is x is equal to 1, y is equal to 2, with the maximum value is equal to 8. Let us go back to the first problem that we formulated and solved earlier by graphical method, that is, consider the LPP, maximize 5x plus 4y subject to the constraints 6x plus 4y less than or equal to 24, x plus 2y less than or equal to 6, minus x plus y less than or equal to 1, y less than or equal to 2, x comma y greater than or equal to 0. We shall solve this problem by simplex method. Step 1. Convert all the constraints except the non-negative constraints into equations. Then we get maximize z is equal to 5x plus 4y plus 0s1 plus 0s2 plus 0s3 plus 0s4 subject to the constraints 6x plus 4y plus 1s1 plus 0s2 plus 0s3 plus 0s4 is equal to 24, 1x plus 2y plus 0s1 plus 1s2 plus 0s3 plus 0s4 is equal to 6, minus 1 times x plus 1 times y plus 0 times s1 plus 0 times s2 plus 1 times s3 plus 0 times s4 is equal to 1, and 0 times x plus 1 times y plus 0 times s1 plus 0 times s2 plus 0 times s3 plus 1 times s4 is equal to 2, where all the variables are non-negative. The variables s1, s2, s3, s4 are the slack variables that are associated with the respective constraints. The first simplex table or initial simplex table is given by, the second simplex table is given by this table, the third simplex table or the optimum simplex table is shown as. Notice that x is equal to 3, y is equal to 1.5 and the maximum z is equal to 21. Now, let us discuss some of the special cases in the simplex method. Sometimes a tie may occur for the minimum ratio. In such cases, the tie can be broken arbitrarily. For example, consider the linear programming problem, maximize z is equal to 3x plus 9y, subject to the constraints x plus 4y less than or equal to 8, x plus 2y less than or equal to 4, x comma y greater than or equal to 0. By computing as usual, its initial simplex table is shown here. Since minus 9 is the most negative among the NER values, dividing the SOL column elements by the corresponding entering variable column elements, we get 2, 2 as the ratios for the first and second row respectively. Thus, 2 is the minimum ratio and there is a tie between these two minimum ratios. Hence, both the rows are eligible to be referred to as a leaving variable rows. If we assume that S1 leaves the basis, then the second simplex table is shown here. Notice that the value of one of the basic variables is 0 in the SOL column and hence minimum ratio is 0. This new solution is said to be degenerate because upcoming simplex table may not improve the objective function value. Now, since S2 row is having the minimum ratio, it is the leaving variable row. So, continuing the iteration, we get the third simplex table, that is optimum. Notice that the optimum solution 18 does not get improved in the transformation from the second simplex table to the third simplex table. This phenomenon is referred to as cycling or circling. Thus, without improving, the optimum solution iterations may carry forward repeatedly, and in any one stage it might reach optimum or it may continue to iterate without reaching the optimum. Thus, cycling or circling slows down the iterative process and hence the solution obtained in the second simplex table is said to be degenerate. We experience cycling or circling because of the redundant constraints. To understand this in a better way, we shall consider the graphical representation of this linear programming problem. Observe that the constraint C1 is not a requirement to get the feasible region. This constraint is called the redundant constraint. Due to the presence of the redundant constraints, the solutions of the linear programming models leads to circling or cycling. The best way is to make an attempt to analyze the given problem and remove the redundant constraints and try solving the problem once again to avoid cycling or circling and reach the optimum faster. A linear programming problem can have more than one feasible point which gives same optima for the objective function. Graphically, when slope of the objective function is matching with the slope of the optimal equation of one of the non-redundant constraints, then the linear programming problem will have an infinite number of solutions. For example, consider the linear programming problem, maximize that is equal to 2x plus 4y subject to the constraints x plus 2y less than or equal to 5, x plus y less than or equal to 4 and x comma y greater than or equal to 0. Notice that the slope of the objective function is minus 0.5 and that of the first constraint equation is minus 0.5. Hence, when the objective function selects the optimum lying on the equation of the first constraint, then the objective function will match with the graph of the equation of the first constraint. Hence, every feasible point lying on this line segment of the first constraint will give the same optimum solution for the given linear programming problem. Now, let us solve this problem by using simplex method, and its initial simplex table is shown here. Here y enters and S1 leaves. Then the second simplex table is shown here. Here we notice that the non-basic variables x has NER as 0, which is an indication that there is an alternative optima in the given linear programming problem. Hence, to find this alternative optima, choose x as the entering variable and continue to iterate to get the third simplex table. The third simplex table is shown here. In this table, notice that NER is 0 for the non-basic variable S2. If we consider S2 as an entering variable, we get back the previous table. Hence, we can consider the last two simplex tables as optimum tables. The optima in the previous table is x is equal to 0, y is equal to 5 and the maximum z is equal to 10, where the optima in the last table is x is equal to 3, y is equal to 1 and the maximized z is equal to 10. These two solutions are the alternate optima obtained through simplex table, which corresponds to the two corner points lying in a straight line segment of the first constraint matching with the objective function. All the points lying in this line segment joining these two alternative optima will form an infinite number of solutions and are found by using the convex combination of 0, 4 and 3, 1. That is alpha times 0, 4 plus 1 minus alpha times 3, 1, where alpha lies between 0 and 1, including 0 and including 1. In this video, we have learned the procedures for the implementation of the simplex method and also learned about the interpretations of the solutions of the given linear programming problem in some special cases of linear programming problems. We shall learn to do more in connection to the simplex method in the next video. Thank you.